This is the Colorsound WAH fuzz and swell pedal. The fuzz and swell works, but the wah is completely dead. So you toggle between the different effects by using the toe switch and the heel switch. And when you enable the wah effect, it goes completely silent. So before taking it apart, we're going to look at the schematic to see what could cause this problem. So first, let's get an overview of the circuit design. Here is the input connector, and here is the output connector. And we can see this little black pin here means that this connector has a switch. And when you connect the phone plug here, this pin will bend slightly and it will close the battery circuit, turning on the device. So the mode of the pedal is chosen by the toe switch and the heel switch. Let's follow the signal path in each case. So in the default position, the signal will come in here through the input connector. Go this way, and it will come to this potentiometer, which acts as a passive attenuator. So it's basically just a voltage divider where the angle of the pedal determines the ratio between the resistor values. This is the output of the attenuator. It continues to the second switch and then it goes out to the output connector. So this is what's called a swell function. It's basically just a variable attenuator. So in toe default and heel default we have swell. So if we toggle the toe switch, the signal will go here instead, and it will go into the fuzz circuit. So at the output of the fuzz circuit, we follow the signal path. It goes back into the first switch and it continues to the attenuator once again. And at the output of the attenuator, it goes out to the output connector. So in this configuration you have both the fuzz effect and the swell effect enabled. Toe engaged and heel default, fuzz. In toe default and heel engaged. Let's follow the signal. Take this way instead. And it goes to the wah board. And this is where we have the problem. And we can see that the wah effect is controlled by the pedal, which we can see with this potentiometer. The output of the wah section is here. We follow it. And it goes straight to the output. So in this mode we have wah wah. And in the final mode where both the toe and heel switches are engaged, let's follow the signal path. It goes to the fuzz section. It comes out here. It goes to the second switch. And it goes to the wah section. And then it goes out from the wah section, loops back in the connector and goes to the output. So in the fourth configuration we have WAH plus fuzz. So let's take a closer look at the wah section, since this is where we have the problem. So you can approach a problem like this in many different ways. This time I'm going to look at the component which I think is most likely to fail. And since this is a quite small circuit, I think that's the fastest way to get results. So we have one electrolytic capacitor in this wah circuit. And since this circuit is made in the early 70s, it's quite likely that this capacitor has dried out. And what usually happens when a capacitor dries out is that it becomes resistive. It essentially turns into a resistor. So let's look at what would happen if we replace this with a low value resistor and see if that could cause the problem we're seeing. So first let's look at the surrounding circuit. At the input stage here we have a DC coupling capacitor and a series resistor. Here we have a transistor and we have a DC bias that comes from this section. So the bias voltage is set with these resistors, which is a voltage divider from the 9-volt battery. It goes through this inductor, through a 1.5 kilo ohm resistor to the base of the transistor. So this inductor here works as a short circuit for DC, but an open circuit for AC. And the reason we have this inductor here is because we don't want the signal to pass through to this section. So if we replace this capacitor with the low value resistor, we will pull this node to ground, and it will have a much lower voltage than it's supposed to. And that means that we will have a lower voltage than we're supposed to at the base of this transistor, which means that it will not turn on. So the incoming signals here, which is likely quite small from the instrument, will probably not have enough voltage to turn this transistor on, which means that the signal will stop here and we will get nothing on the output. So it's quite possible that this is actually where the fault is. To verify this, we will measure the base emitter voltage of the transistor. So the base emitter voltage of a transistor is usually 0.7 volts, so that's what we're expecting to find here. But if this capacitor is bad, we will likely have a much lower voltage here. So, since I did not have the layout of this circuit board, I had to map the schematic to the layout manually. And while doing so, I found that this inductor was not connected in one end. So let's see if that could be the cause of the problem. If this inductor is gone, we will have no DC connection between this point and this point. And since we have a capacitor here, we will have no DC voltage going from this node to this node. So from a DC point of view, this node will be floating, and therefore there will be no stable DC voltage at this node. So I reconnected the inductor, and we will now measure the base emitter voltage of the transistor once again, and hopefully it is a bit higher this time.